If you want to get from the top floor of your house to the bottom, building a slide could be fun, but highly impractical. You really should take the stairs. In the field of voltage converters, for years everyone has been going from the top floor to the bottom floor the hard way. Today, Murata is taking the stairs with their new two-stage converter designs. Joining us today is John Barnes, the Distribution Sales Manager for Power Products at Murata. Thanks for joining us, John.
Thank you.
Now, buck converters and voltage regulators have been around for quite a while, but you have some new concepts that you'll be teaching us today, correct?
So today we'll be introducing a new family of fully integrated buck regulators named Ultra BK, which is our MYTN series. And this new product is a next generation power module that uses a two-stage architecture patented by Murata, which employs a switched regulator technology and enables very high efficiency with a low profile. So just want to show everybody what the agenda is for today to solve a problem, provide an overview of this two-stage architecture, along with product highlights and key takeaways. Okay, so here is our problem to solve. In this example, for a PCI Express card installed in a data center. And just to go through the different colors, the red zone is power conversion. Typically, power conversion can occupy up to 50% of the total board space. The inductors are in the blue outline, the dotted lines, can typically be the highest components in the system.
Yeah, that component height can be a really critical aspect for airflow and associated cooling. I saw some research recently that said 30 to 55% of a data center's energy consumption goes into powering the cooling and ventilation system. So that height and how it affects cooling can have a big impact on operating costs, and those lower board temperatures will improve reliability and product lifetime.
Right. And anything we can do to improve efficiency and reduce heat generated in the system or improve thermal performance is going to help with their overall system operation.
Absolutely.
And then just going to the back side of the PCB, there are also many components on the other side. And with all these components, we can see a generation in noise and ripple as well. So, and we'll address that with the Murata solution.
Yeah, and expensive. That's not just the cost of the components, but that's the board real estate, the operating costs, all those things are a factor here.
Absolutely.
Yeah. And now you're going to show us a new solution to this old problem.
Yes. So we'll go into the next stage, which is to talk about Murata's technology and how we can solve some of these problems. So the solution Murata is introducing is a unique two-stage architecture. And in this example, we will take a look at a traditional 12 volt to 1 volt single stage conversion, which is very popular in server applications. Normally there would be a single buck regulator converting from 12 volts to 1 volt. And in this case, there is a huge dependency on the inductor, which is doing the heavy lifting. And this is why a larger inductor is typically used and takes up more space, as well as increasing the height of the inductor. So we'll see some of the problems that are caused by low duty cycles, including poor efficiency and poor transient performance, as well as large ripple that you see in these traditional type single stage converters.
Yeah, switch capacitor circuits have been widely used in filtering and analog to digital converter designs for decades, really, but using them for power conversion is not something I think I've heard of before.
Okay. Well, this technology is very interesting because in the two-stage solution from Murata, we are offloading a lot of the work from the inductor by adding a virtually lossless charge pump in front of the buck regulator. And the purpose of the charge pump is to break down the relationship between the input and output voltage. And since the capacitor is doing a lot of the work instead of the inductor, this greatly reduces the inductor size and the inductor height. And the charge pump provides a lower input voltage to the secondary buck converter, which is what helps to reduce the size of the inductor in that secondary stage. This allows for the use of lower voltage FETs for all the power rails and improves efficiency and reliability as well.
Yeah, it's interesting. So tell us more about the advantages of this switch capacitor solution and changing from having those inductors do the heavy lifting to forcing that over onto the capacitors.
Yes, absolutely. So if we look at the problem with inductors, the inductor can be the biggest enemy in our system. So we need to find a way to minimize dependency on the inductor. And here's an interesting comparison between capacitors and inductors. Capacitors have 400 times higher energy density as compared to inductors. This means that the capacitor is no longer just used for decoupling or filtering purposes. It is part of the power conversion process. And Murata's new two-stage architecture is a major innovation to the power industry.
Yeah, this is really interesting. It almost seems like you're comparing apples and oranges with a traditional engineering view, because engineers think of capacitors and inductors as completely different devices, and they're used to perform different functions. So we rarely directly compare inductors and capacitors because they're solving different problems. But here, Murata is using capacitors to solve this problem that's traditionally been addressed by inductors.
And that's a good point versus the traditional use of capacitors and inductors. But let's take a look at the comparison here, the left side being a traditional single-stage buck. If you only have a buck regulator, all of the FETs are rated for that input voltage, in this case 12 volts. And these higher voltage FETs increase switching losses and cause poor efficiency. And the inductor does all the work, which requires a larger size and a higher package and causes poorer transient performance and requiring more output capacitance. The input side requires a larger filter to address EMI, causing poor duty cycle operation. So looking on the right side is Murata's unique two-stage solution, where we're using capacitors on the front side of this, or the first stage, with a charge pump technology. And so the voltage transition within the charge pump can be considered as a staircase. And this enables the use of low voltage FETs to achieve higher efficiency and reliability. The capacitors are doing most of the work on the front end of this two-stage solution. And this significantly reduces the size, including the input and output filtering required, and provides better EMI and transient performance with this unique two-stage architecture.
Yeah, it's really interesting. So instead of biting off the problem all at once, kind of take a lot of little nibbles to solve this issue.
Right, right. I mean, we basically are taking the voltage down in steps with the charge pump, and then the input to the secondary is typically 4 volts, which puts a lot less work on the inductor on the secondary stage.
All right, what are some of the other benefits of switching to this two-stage architecture?
Okay, it's a very good question. Another benefit from this new architecture comes from the two-phase interleave operation of both the charge pump and the buck stage. The interleave charge pump stage leads to lower input and lower EMI noise, and also the interleaved output buck leads to lower output ripple and better transient performance. This is a significant advantage as it reduces the total solution size, including the number of external components.
As noted previously, the output voltage is often as low as 1 volt these days, and so reducing that ripple is very important for reliable operation of those downstream systems that are relying on the power. So if that voltage goes too low because of the ripple, the system stops functioning correctly, and if the voltage spikes up too high, the system could be damaged.
Right, right. It's a major benefit that in this instance, we're reducing the voltage from 12 volts to approximately 4 volts. And so the input voltage on that secondary buck is much lower than would be typically seen in a standard 12 to 1 volt buck converter.
Exactly. So now that we've discussed this new voltage regulation concept in detail, why don't you tell us some more about the specifics of your Ultra BK products?
Okay, yep. So product highlights on the inside of the Ultra BK 6 amp module. The Ultra BK is the world's most efficient low profile, fully integrated buck converter. This part was created with vertical integration of Murata's technology, including the silicon and all the passive components, including Murata's X7R series capacitors and multilayer chip inductors. So we are very vertically integrated with this technology. It also leverages Murata's packaging technology, and this integration enables 50% smaller solution size, 25% lower profile, and a 10% efficiency improvement, as well as 20 dB lower EMI and 4 to 5 times lower input ripple. So it's pretty significant what we're able to achieve here.
Yeah, those size reductions in X and Y is something we hear a lot about, but the Z dimension is often forgotten. But that means squeezing boards more closely together or improving cooling efficiency. And then that efficiency improvement of the regulator itself means you're generating less excess heat during that conversion process. So it's kind of a multiplying effect in improving efficiency.
Right, right. So some of our other solutions have a Z height that is closer to 5 millimeters. And you can see with this module, it's 2.1 millimeters. So we really are able to provide a much lower profile with this two-stage architecture than is typical for this type of product.
So what is P Semi here in your patented hybrid power IC chipset?
Right. So P Semi is a wholly owned division of Murata, which they design RF ICs as well as power ICs. And so for this product, Murata actually designed the silicon technology for the controller.
So even though this looks like a kind of a printed circuit board, this is actually stuffed into a single package solution, right?
So yes, this is a packaged module, and it includes a substrate with the components and then an overmold. So if we look at this, the product family is targeted for a 12 volt in point of load application and includes a front end divide by 3 charge pump. So the front end of this solution is not regulated. So depending on the input voltage changes, the output of that first stage is divide by 3. So it's like a turns ratio with a transformer. And then the secondary stage provides the regulation for the output. And then both the 4 amp and 6 amp parts use the same package footprint. This supports the increase in power demand with the need to respin printed circuit boards. And these parts have an option for I2C communication. And both the 4 amp and 6 amp parts are released and parts are available with Mouser.
So you use a number of comparative terms here, highest, low, fast, and the marketing folks like to use those terms, but help us out as engineers. How really do these Murata products stack up against the competition?
Sure. So here we'll give some comparative charts for several of these metrics. And so here we're comparing our 6 amp part performance to a competitor. And so overall, our solution size is 50% smaller and the height is 25% lower since our parts use a very small chip inductor. Typically, a smaller and lower profile solution will sacrifice performance, including efficiency. However, with the size and height of Murata's module, we can achieve higher efficiency, as you can see in the left quadrant, upper left quadrant there. better transient response, which you can see in the lower left side with 60% less output capacitance, and then a 40% improvement in input ripple with zero input capacitors and improved conducted and radiated EMI. And you can see the CISPR Class B line there, and you can see in the upper right-hand corner the blue spectrum on the left side and the red spectrum. You can see some of the peaks exceed the CISPR Class B with the competitor, as well as our overall profile for the radiated EMI is better than the competitor.
Yeah, that's some impressive performance. What really jumped out at me is that input ripple improvement by removing the input capacitance. It's almost magic. It's contrary to that standard rule of thumb engineers use. If you got to get rid of the ripple, add more capacitance.
Right, right. So yeah, it definitely shows a significant improvement in ripple, and with a lower overall height makes it pretty impressive.
Where are you seeing interest in applying this two-stage converter solution?
Good question. So this shows some of the target applications for the Ultra VK. One of the best examples is for PCIe cards, which include FPGA, ASIC, and memory into the industry standard form factor. The need for many power rails can lead to serious space issues. So here's a list of other high density applications that can benefit from our two-stage architecture, typically having large V in V out ratio, which creates lower duty cycles that can be solved with our charge pump technology. Another example is the micro MIMO for 5G using RF components that are very sensitive to noise. Our solution can address the CMI issue and can reduce the cost of their overall power and filtering solution.
These images are great examples of space constraints. They impact almost everything. In every one of these applications, people are trying to stuff more computing into ever smaller spaces, but you still have to deal with that power. You have to control the heat generation and the RF emissions, and your power converters are going to help all those things.
Right, and we're seeing more and more of these type applications where a smaller package can really help. Here's an example that shows how the Ultra BK was able to solve a problem for a PCIe accelerator card. On the top there, you can see the previous solution, and with a very tall inductor and the need for a heat sink that restricted airflow. By switching to the Ultra BK, we're able to eliminate the tall inductor and improve the overall airflow through the space. So this was definitely a big improvement, which saved space, improved airflow, and did not sacrifice efficiency or thermal performance.
Yeah, for a little context on how big of an issue cooling is, I saw recently that a single Google data center can use up to 4 million gallons of water every day. That's 6 Olympic-sized swimming pools just for its cooling. And think of that energy required to circulate that water, cool the building, and then ultimately what they're trying to do is drive cooling air across their PCBs and their server farms. And so even a 1% improvement in cooling efficiency could be huge. I mean, that'd be 40,000 gallons a day, which is about the amount used by 500 homes. So these kind of improvements in airflow are a big deal.
Absolutely. And the other thing I should have mentioned is because of the low profile of the Ultra BK, there is an option to mount the component on the back side of the board and not take up space on the top side.
And so, John, your opening slide described this as a series of regulators. So what products are available in this series?
Right. So this just shows the product lineup for today. There is a 4 amp and a 6 amp, and they come with or without the I2C communication. If you use the module without the I2C, the output voltage can be adjusted with an external trim resistor. And all parts have the same input and output voltage range. It's just an option of whether or not you prefer the I²C.
And it looks like with that I²C communication, you get some telemetry data as well.
Right. So you can monitor the part, and then there are some, you can adjust the output, trim the output voltage with the PM bus. And then there's a complete app note that explains how the I²C can be used with the product.
All right, John, we're getting near the end of our time here, so wrap everything up for us.
Okay, so this slide just summarized the key takeaways for the Ultra BK. And so looking again, Murata uses a two-stage architecture with charge pump technology, which allows for the highest efficiency in the smallest overall space, and as well as using low voltage CMOS for high reliability, and providing very low ripple and EMI to minimize overall external components and overall cost. So the theme of today's presentation is Go Big by Going Small.
Clever. Did you come up with that one, John?
No.
John, thank you for meeting with us today to discuss this new two-stage concept for voltage conversion and the Ultra BK buck regulators from Murata.
Okay, well, thank you. I appreciate your time, and hope everybody has a great day.
Yeah, and before I let you go, though, I have to ask a question that's probably on everyone's mind as we look at this last slide. What are we looking at here?
These are the Murata cheerleaders, and if you go to trade shows, I think they're like about 12 inches tall, and they utilize Murata's technology, and so they actually all start in unison, and they turn and they spin, and it's all done wirelessly, and also uses some of Murata's sensor technology to keep them from falling over. So they actually sit on those balls. So the balls are not attached; they're just rollers. It's pretty cool.
Oh, very cool. Yeah, I was kind of getting a kind of a modern take on the old Rosie the Robot from the Jetsons cartoon from the 1960s.
Right. You can go to YouTube and type in Murata cheerleaders and watch the video. So there's several there. It's pretty cool.
All right, very good. All right, thanks again, John, for joining us, and I hope we get a chance to talk again in the future.
Okay, thank you. Bye-bye.